Okay, hello everyone. Welcome to Provenance and Guidance. My name is Alvita Otley, and I'm from Washington University in St. Louis, and I'm going to be chairing the session. I'm also accompanied by Shayan Monajami, who's also going to be helping me manage Slido and ask questions. We're going to kick it off with the first paper for the session. This is the influence of visual provenance representation on strategies in a collaborative handoff data science scenario, and this will be presented by Jeremy.
Hello, everybody. My name is Jeremy Block, and I'm presenting this work on behalf of some of my collaborators from the University of Florida, as well as those from Oak Ridge National Laboratory. The work has a pretty long title, but the thing that I want to focus on here is collaboration. In our current work practices, it's not hard to imagine a scenario where you might be working with someone else. For example, you might have doctors working with nurses, or a user experience practitioner working with software engineers, even a researcher presenting work at a conference. Our work today is very much collaborative, and everything that we do is inherently collaborative in what we are working on. And it involves someone explaining something to someone else. But this communication is not always easy. There are questions about what content should be included in a message and how we might explain that content to others. When a nurse tells the doctor something, it's not always clear where that data may have come from. How do they know what they know? And what did they review along the way? And what steps did they take to draw that conclusion? Enter provenance. This is an idea that helps aid in communication because it focuses on telling the story of where something came to be. Originally applied to artwork like the Mona Lisa, it explains the story of where something was or who owned it over time. But provenance is also applied to concepts and ideas that describe the insights of a data analyst who might develop while they're reviewing data. So by providing provenance, we allow others to review and reveal what was considered or not considered when developing those new ideas and solutions. Yet when we talk about provenance, knowing where to start is challenging. Depending on the level of detail, there may be an infinite number of steps that need to be explained. Do I start from where the materials are from? What actions should I describe? What does the listener already know? This is overwhelming for new users and requires summarization. There is an art to a well-designed provenance. Much like a good movie director, they know what scenes tell the story most effectively. And although designing provenance is an ephemeral art, it holds promise in numerous collaborative settings, and we need effective ways to generate usable provenance information automatically. In the literature, there are two fairly standard classes that help to generate provenance automatically. I refer to them as interaction history and data coverage. Let me explain them a little bit more detail. The first is implemented in this interface for lighting designers. It captures the scene over time and shows the past stages of their design for a room. By visualizing their interactions, they can see a history of their past attempts and what interactions they had when they made changes. So you'll see that on the bottom there. An alternative approach is to use data coverage, where you show what data was interacted with most frequently. In this example, data can be dropped into a visualization, and the bars next to each column title show how frequently that data has been used by others. This way, other people know what data has been explored most often and where they can look next. Oh, I forgot the arrow. There's the arrow. But how do these approaches compare? And what are their impacts on collaborative data analysis? Currently, there are no empirical evaluations to explore this question, especially in areas with lots of collaborations and concerns about data sharing, such as an intelligence scenario. So since provenance is designed to help people understand what has been done, how do people actually use these different approaches when they do a handoff of information from one group to another? So that leads me to our research question. We designed an experiment to understand how provenance representation may impact an investigator's behaviors and strategies in a data handoff scenario. We designed a proxy textual intelligence analysis task with provenance representations of a prior analyst. Participants were given a collection of text documents and asked to solve this mystery. The data consisted of fictional worldwide news articles, and they could search for and read different articles to piece together all the different pieces. As a control, all participants were given a brief textual description as if somebody left a note on their desk saying, "Hey, could you work on this?" The memo recommended a handful of entry points to approach the analysis and help to control which tangents people paid the most attention to. We also had the history condition. This showed specific search and highlight events summarized into groups of activity. This segmented timeline helped to establish interaction order and how much time the prior analyst had spent doing the analysis. The alternative condition was this coverage condition, where we showed what data was explored by the prior analyst, and the pink bars helped to reveal where it had received the most attention. And we had a couple of hypotheses. For example, those with the history condition would be encouraged to follow the prior analyst's work, thus spending more time verifying and checking if there were any errors, while those with the coverage condition would be encouraged to forge their own trail because it emphasized the areas the prior analyst had already worked on or where they had already avoided. So the experiment consisted of a scripted tutorial, a 30-minute data exploration task, and a follow-up interview to see what participants understood after working with the data. We ran this with 36 participants from an upper-level computer science course, and the experiment was run virtually over Zoom during the pandemic with Zoom rooms as well as screen shares. And since we were using our own software, we could track all sorts of interactions, some of them including opening the documents or which documents were opened, what things they were searching for, things of this nature. And this way we could get a better picture of what behaviors they were doing. One behavior I want to draw attention to is how participants revealed and gathered information. They used the search or clicking in that provenance tool to filter the data. And this is one of the first results that I want to draw attention to. So what I'm showing here is the rate of filtering by participants that they complete in their 30-minute window. So the x-axis is the 30 minutes of time, and the y-axis is what percentage of their filtering they have completed. So each faded line in the background is an individual, and almost all of them complete 100% of their filtering by the end of their session. So we're showing individuals' rates of filtering. Basically, we would expect no difference in when filtering occurs across the conditions. Instead, the thicker trend line shows that those in the history condition completed half of their searches before the halfway point in the analysis time allotted. In contrast, those in the other conditions did most of their filtering later, when they probably had a better understanding of the data. This significant difference suggests that those in the history condition had shorter dwell times on each document and spending more time gathering information and not as much synthesizing or hypothesizing what results may exist. The other result dealt with the strategies we observed from our qualitative review. Based on the strategies identified by Zhao et al., we saw supporting evidence for the different analysis strategies. In our work, we saw these 4 strategies, and I'll explain each of them now. Keyword browsing refers to someone who spends time planning and hypothesizing and then enacting that plan as they work through the data. Random access describes participants with a less structured analysis plan, and we're clicking randomly, kind of finding data serendipitously. We also see reviewing the origin, where somebody verifies what has already been done, like we had predicted with our hypothesis. And then we have the starting over group, who intentionally put aside the work that the prior analyst had done and do their own independent analysis and then check their work later. And what's interesting here is that none of these investigation strategies align with one of the design conditions. This tells us that the provenance representation does not significantly influence one's strategy and is more likely related to a different factor, like individual differences. So in conclusion, provenance representations can be helpful for analysis tasks when they are provided at the appropriate level of detail. This is to say that since those with the coverage or control group were given a high-level overview of what happened in the prior work, they can jump in more independently. In contrast, those with the history condition had a description of all the steps and documents encountered over time. In a way, this interface introduces an alternative sense-making task where participants guessed what the prior analyst was thinking when they triggered each action. This takes more time to review, requires more data filtering, and leads to more gathering-like behavior. Therefore, our results imply that the provenance summary that reduces the complexity of prior analysis are beneficial for handoff scenarios. Additionally, we do not see strong effects on the analysis strategies. This implies that provenance representation does not directly influence how people attempt to work with provenance in a handoff scenario. Since the provenance representation does not influence the strategy, having these features available will allow for additional diversity in how people try to solve problems. Ultimately, our results imply that provenance summaries that reduce the complexity of prior work are beneficial for handoff scenarios, but having provenance available does not generally influence how people work on data analysis tasks. Thank you again for listening, and let's try to continue creating different summarized versions of provenance. Thank you.
All right. Thank you, Jeremy, for a great talk. We got 2 questions on Slido. Well, we just got the third one. So the first one is by Jordan Cruiser. Nice talk. How did you select your conditions and set up interactions to record? Are there others you would add if you ran this experiment again?
Yes. So when we are looking at these conditions, what I was looking for is in a prior analysis and kind of literature review, I was looking for what are some common approaches for representing provenance. And these were 2 that stood out fairly well. There are additional ways, like doing a graph-based example of provenance. We did not include that, mainly to try to do something simple first and just to see what was going on, because we hadn't seen any other evaluations like this. So we could do other ones as well, but for now, we focused on these 2 because they seem pretty popular and fairly simple.
All right, thank you. So I'm going to ask another question, and then the rest are going to be on Slido. So the next one is by Mi Feng, asking, curious about your thoughts on testing out the combined conditions, like data coverage plus control or write-ups, to see if it would outperform the individual conditions.
So the control condition was provided to all participants. So everyone had the ability to have that kind of summary. It would be interesting to just do one of them as if we just provided coverage or we just provided history. But I think that the combination of having just a summary at first helped us to control what people were looking at. The qualitative review itself was actually very challenging with this problem because anyone could do whatever they wanted with the data set, and there were more than 100 documents to work on. So there were lots of concepts that people could play with. So by having that control condition available to start with, it helped to kind of guide the users. So I think that in general, having trying different approaches would be another approach as well.
Thanks, Jeremy. Let's thank our speaker again. Okay, so our next speaker will be joining us virtually, and the next talk is understanding how in-visualization provenance can support trade-off analysis. And this will be presented by Mehdi.
Hello everyone, my name is Mehdi Chakchouk. I'm a second-year PhD student at the Université Paris-Saclay, and today I will be presenting the work we conducted in our paper about understanding how in-visualization provenance can support trade-off analysis. A lot of real-world problems are actually multi-criteria decision-making situations where there is no clear-cut best answer. For example, choosing wheat fertilization strategies, studying the sustainability of ecosystem services, or wine fermentation recipes requires the experts in those domains to make trade-offs. Let's take wheat fertilization, for instance. When choosing wheat fertilization strategies, experts have lots of objectives, like minimizing the fertilizer doses for economical and environmental reasons. They want to maximize the yield, of course, but they also want to reduce the impact on the environment, and they also want to maximize the quality of the wheat, etc., etc. The problem is that if we minimize the fertilizer dose, then the yield will get minimized as well. And if we maximize the yield, then we also increase the impact on the environment. These objectives are conflicting. Now, reaching an acceptable trade-off between 2 or 3 objectives is doable and relatively easy. But real-world problems are often way more complex and can involve dozens of dimensions, some of which are conflicting objectives. In the case of wheat fertilization, mentioned before, our experts wanted to examine tens of dimensions at the same time. In the past, one way to solve these problems was to gather a group of experts from different fields with different expertise. Some are biologists, agronomists, or optimization experts. They would come together around a visualization tool, explore the data, and choose solutions. The way these explorations would go is experts would bring their data that is often derived from models simulations, big data sets of thousands or hundreds of thousands of points where each point constitutes a potential recipe or solution. One possible way to go about this is to first use some mathematical optimization, like a Pareto front, for example. This would generate a group of points where no objective can be improved without sacrificing at least one other objective. And the size of these sets of points would typically be in the hundreds or a couple of thousands of points. Then we plug this data set in a visualization tool to explore the data and come up with good trade-offs. Now, the issue with such an approach is that the exploration sessions tend to last several hours and span over the course of several weeks, months, or years. So the experts will get lost in the explorations and they have a hard time remembering the results they found, how they found them, and how to reproduce such findings. And so the solution we decided to explore was to use analytical provenance visualization to support such trade-off explorations. This has not been studied in the context of decision-making in trade-offs. And the reason we need visualization for logs is because otherwise they are unreadable for most people. Previous work has shown that provenance visualization can help data analysis and exploration. But the question we are asking here is, can it help trade-off analysis specifically? Because trade-off analysis is a particular type of data analysis. What's particular about trade-off analysis is that you need to keep track of competing objectives, you need to keep track of the objectives that need to be maximized and minimized, and you need to compare different alternatives to select the best trade-off. The goal of the experiments was to explore the use of analytical provenance visualizations to aid experts keep track, resume, and revisit their trade-off analysis sessions. And the way we did this is we first created a probing tool, then we conducted experiments with this tool, and finally we analyzed the results from the experiments. This is our probing tool, VisProm. It's an online visualization tool that uses lightweight in-vis provenance that is always there during the exploration to support trade-off analysis. And here are some of the provenance views we have implemented. The red borders in the scatterplot matrix show what you have visited and what is left to visit. The more you visit a cell, the more opaque the border gets. We have a table that shows you, with blue bars, the amount of visits you do for each dimension. We have a table that informs you where the points from a selection fall under each dimension. Here, for example, the red selection minimizes the T0, E0, Pmax, and TFM dimensions, while it is in the mid-range of N0, IAA, EH, and one of the composite dimensions. Now, the way we conducted the observational experiments was by asking groups of experts to conduct their data analysis tasks with their own data sets in our tool VisProm. First, without the provenance visualizations mentioned before, for a session that lasts about an hour and a half. And then bringing them back weeks, months, or years later to recreate, then resume their past exploration. This time, with the provenance visualization from their past and current exploration enabled. So in our paper, we discussed the trade-off tasks that our study participants engaged in. We introduced provenance objects, more on that later. We report on how provenance was used during trade-off analysis, and we discuss the provenance opportunities in trade-off analysis. Since we need to keep this presentation short, today I will only talk concisely about these two aspects of our contributions. For more details, please read our paper. As mentioned, we identify provenance objects that refine provenance purposes by adding subcategories and concrete specifications for real-world trade-off analysis. Basically, we are trying to answer the question, what do our experts want to, blah, here to support trade-off analysis, where blah is provenance purposes from Regan's previous work. Here are some of the objects we came up with. For example, interest zones is about understanding what are zones of points that represent trade-offs. Focus on priority is about remembering which objectives are the priority. For example, do experts care more about yield or the impact on the environment? And has this changed over the span of the exploration? The reason provenance objects are important is because they are the aspects of the analysis that we want to pay attention to as VIS designers when we create designs for provenance visualization in trade-off analysis. When it comes to provenance use in trade-off analysis, the tool was reported as useful by experts, not only to remember past explorations, but also as an exploration aid during the exploration. In our paper, we discussed the fact that provenance was used for past exploration and present for different purposes. These findings show, of course, that in visualization provenance is very useful, but we go beyond past work that uses in-vis provenance by characterizing when and why the different designs are useful. For example, which designs are best for past and which for active exploration, and for which purposes. Okay, to summarize our paper, we used VISPROM as a technology probe to conduct observational studies from which we reported on trade-off tasks, we identify provenance objects, and discuss the use of provenance in trade-off analysis tasks. And finally, we provide a discussion on the opportunities for provenance in trade-off analysis. Thank you for your attention. For the paper and our analysis code, please visit our GitHub.
All right, thank you so much. Really interesting work. We have one question here on Slido. Did you find the analyst had time to work with the provenance objects, or were they primarily focused on performing the core data analysis tasks? For example, rearranging, editing dead ends, or adding explanations to their choices?
Okay, so it mostly depends on the analysts. So some analysts are very, very focused on their own data and their tasks. So they just use provenance if they think about it and whenever it can help them. And some other analysts are more, try to be more structured and want to take notes or like annotate stuff. And so it depends mostly on the analysts. And my hunch would be it would also depend on the field and the way analysis in the field happen usually.
Okay, thank you so much. I mean, really great work. It's really awesome to see these kind of longitudinal studies. And so I think this is a great contribution to the community. Thank you again. Let's thank our speaker.
Thank you.
Okay, so our next paper is going to be another virtual presentation. It's called Provectories, Embedding-Based Analysis of Interaction Provenance Data, and this will be presented by Connie.
Hi, my name is Connie Wasserfer, and I'm a PhD student at the Johannes Kepler University in Linz in Austria. It is my pleasure to present the work that I've done with my colleagues in the last years about provectories, an embedding-based approach to analyze user interaction provenance data. The word provectories is actually a great acronym and consists of 5 characteristics. First, we analyze interaction provenance. Second, we use different layouts to understand the analytical reasoning process and patterns with topology and attribute-driven layouts. We therefore have to prepare application states as feature vectors before understanding the user sessions. And each interaction is represented by a point in the embedding space and the sequences via trajectories. Finally, stories are the output of single and multiple user sessions that we analyze. I will introduce you now to our approach by using the Gapminder dataset. The data shows the development of countries over time. While interacting with the bubble chart, where each country is represented by a colored mark, each interaction, in this case each click event on either the axis assignment or the country, can be stored as a temporal sequence, also known as a history graph. This means that each application state can be exactly described by the x-axis, y-axis, mark size and mark color, the selected year, and any country selected by a user. Therefore, the timestamp T5 is represented by the respective attribute selections. To visualize the sequence, we were therefore interested in the differences and insights that we can gain from topology-driven layouts, which emphasize the connectivity between identical states, and attribute-driven layouts, which focus on the similarity between states. For the topology-driven layout, we used a force-directed algorithm, and for the attribute-driven approach, we used t-SNE, multidimensional scaling, and UMAP. To get to the connectivity and similarity-based visualizations, we first have to transform all non-numerical dimensions into a numerical value, since high-dimensional data analysis methods are primarily based on vectors with numerical attributes. We chose a one-hot encoding that encodes the value of such dimensions as vectors. As outlined, the interaction state T5 shows a change on the x-axis by changing the attribute to GDP. Finally, for the purpose of meta-analysis, each user session can be visualized as a trajectory through a 2-dimensional embedding space connecting the application states. Thus, country selections are represented with a topology-driven layout as a normal sequence, and in contrast, the 3 states, 2, 3, and 4 on the right-hand side are closer to each other using the t-SNE projection. To demonstrate now the applicability of provectories, we first created synthetically generated sessions to understand data type-specific patterns in the 2-dimensional embedding space. We then describe observed patterns of 2 user studies representing actual analysis provenance. With the synthetically generated sessions, we could identify 2 distinct areas in the embedding space for the categorical attribute mark color. It consists of 2 attributes where the attribute religion is represented in orange and the continent in green. For categorical changes with more attributes, first a cluster forms, in this case for the x-axis in the embedding space, and the respective axis assignment attributes form a zigzag pattern. For instance, GDP is colored in orange and life expectancy in pink. In contrast, as t-SNE attempts to preserve the high-dimensional distances, circular arrangements for single selected countries become visible, leading to a ring pattern for a combination of single and multiple selected set attributes. In session A, as outlined here, we can see that at the beginning that no country was selected, then one country was added and a second was selected by the user before deselecting both countries again. Lastly, the distance between 2 states, A and B, can be calculated as the weighted sum of all individual attributes, or attribute distances. Therefore, when varying the weight and increasing the weight for numerical and set attributes, hierarchical representations emerge. At the top, you always see the projections in the embedding space, and at the bottom, you see the summary visualizations for the given data. At first, a Boolean distinction becomes visible before the categorical sub-hierarchy for the size encoding emerges out of the orange cluster for religion. Within this subcluster, further clusters such as GDP, child mortality, or fertility emerge. After getting a good sense of pattern for pattern recognition with our synthetic stories, we applied the detection to actual user data from a user study, also using the Gapminder dataset. We were able to confirm the observed patterns for all 4 data types. But as our intent was to understand the user's analytical behavior, we were not only interested in a single user session, but multiple users conjointly in the same embedding space. So when first analyzing a single user session, starting from the purple cross and ending at the light green star glyph, analytical strategies such as a verification loop leading back to an already selected state and alternations, which is a toggling between 2 states, for instance, selecting either this or that country, becomes visible. And when taking a closer look at multiple user sessions in the same embedding space, it becomes apparent that participants do not exactly use the same way to answer questions. Moreover, they tend to choose quite similar ways, which is visible actually in the embedding space by conceptually similar states close to each other and overlapping trajectories. For the second user study, we used the data from a user intent study. In this case, for instance, for a cluster task, participants had to select all data points that belong to a specific cluster in a scatter plot. We visualized these user interactions using the Projection Space Explorer and applying the Provectories approach. For an easy cluster task, few data points and overlapping trajectories are visible, meaning that the participants followed a similar path for solving the task quite quickly and by selecting all data points belonging to the look cluster. In contrast, when taking a closer look at the projections for a more difficult task, numerous unique data points become visible and hardly any overlapping trajectories are identifiable. This means that scarcely any participant followed the same solving strategy. Additionally, and it's highlighted here as a ground truth state and it is colored in orange, it actually represents the correct selection of all data points in a scatter plot belonging to a cluster. As you can see here, in a more difficult task, this was never met by any participant at all. So additionally, what we also noticed as a side effect was that people actually started to select outliers for an outlier task, for instance, from top to bottom and left to right. This corresponds to a reading flow of a book. And to demonstrate the applicability for an outlier task additionally, you can see here the data point distribution from the scatter plot at the very beginning at the top left. And on the right-hand side, you see the embedding space or the projection where we stepwise analyzed these visible clusters where we connected them in the embedding space. So there we could identify and report on the differences between the 2 states as outlined here as a cluster A until H. Additionally, and as the feature vectors for our Provectories were tailored to the given studies, we saw this as a limitation, and therefore we are currently working on an approach for generic purposes using interactive dashboards for Microsoft Power BI. Power BI is actually a feature-rich tool, and the feature vector length as well as the complexity can vary depending on the visualization types and interaction techniques used. Moreover, to combine the advantages of both the topology and the attribute-driven layouts, we have started to develop a hybrid layout approach. So overall, with Provectories, we have demonstrated a novel visual analysis approach to extract patterns from interaction provenance data. By interactively exploring such visualizations for compound representations in real user sessions, patterns based on data types and analytical reasoning processes can be revealed. I cordially invite you to check out our paper and the application via the QR code on the slide. Unfortunately, I cannot answer your questions because our baby has either already seen the light of the day or will see the light of the day in a few moments or days. However, my colleague Andreas Hinterreiter is happy to discuss the ideas and questions online, and my contact informations are on the slide. So thank you for your attention.
Well, congratulations to Connie, hopefully. There is one question here.
Yes. Could you please tell us more about how you generated your synthetic data?
Yeah, sure. That's a good question. So we thought about the different patterns that could be in real data, like when users go through, there's this step interface for the year, for example, in the Gapminder. We thought users might go through the years one by one, or different patterns when it comes to the selection of countries in the scatter plot. So we thought about these different patterns and just created these artificial stories or user interactions that had some of these patterns. And the idea was just to get a feeling of how those patterns would later look like in the visualization. So they are definitely not complete, but they helped us a lot in understanding the patterns that we can see in the Provectories visualization.
All right, thank you very much. Well, actually, we just got one more question on Slido. How do you interpret the results of your tool? How do you use the tool to actually find insights about the specific activity followed by users?
Mm-hmm. So to fully understand this, I would encourage you to check out the interactive prototype, because then a lot of things become more obvious. We explore these visualizations interactively with a lot of different layout enrichment techniques, like encoding the data points by different attributes from the original visualization, and also by summary visualizations that summarize individual data points or clusters of data points. And then we discover these findings by just going through those, by performing this visual analysis interactively.
All right, so one last question that we have to ask this question. Has the baby been born?
I don't think so, no. I think she's still waiting.
All right, thank you very much.
Thank you.
Okay, let's thank our speakers. Okay, so our next paper is another virtual talk entitled LOTSE, a practical framework for guidance in visual analytics, and it's going to be presented by Fabian.
Hi everybody, I'm Fabian and welcome to my talk on LOTSE, a practical framework for guidance in visual analytics, work that I've done together with Davide and Menna. A few years ago, here at Viz in 2017, Davide and his colleagues defined guidance as a computer-assisted process aiming to resolve knowledge gaps that users encounter during visual analytics sessions. They've also shown how guidance integrates into the visualization model by Van Wyk. However, there are now several other representations of guidance and theories that focus on different aspects and have different visualizations. As a result, it's easy to get lost as a newcomer when deciding how to implement guidance without knowing where to actually start. In this paper, we present a strategy-based model of guidance that we believe is much closer to actual implementation practices. Before we have a closer look though, I'd like to take one step back and describe what we mean with a guidance strategy. A guidance strategy encapsulates an individual solution strategy that a user might have during a visual analytics session. And because visual analytics tasks are typically not super easy, there's quite often multiple competing strategies for a given problem that all lead to potentially different, but also potentially equally good solutions in the end. If we imagine this very simple example here of a few data points that we would like to cluster and an initial clustering result that we get from an algorithm, then we could, for example, as a strategy, suggest to add more data points to the blue cluster to make it homogeneous. Or from the same starting point, we could suggest to remove data points from the blue cluster to introduce a clear separation between the blue and the green one here. Of course, the number of guidance strategies here is potentially endless, and we could suggest all kinds of things, switching to a different clustering algorithm from dbScan to k-means or the other way around, or just changing a few algorithm parameters. The task for developers of guidance systems then is to specify, well, their initial assumptions of what strategies will be helpful when, and equip the system also with functionality to learn and adapt to the user based on the relevance feedback that it can collect over the analysis, during the analysis. If we imagine the state space of an analysis session as this rectangle here on the bottom of the slide, Then developers essentially place guidance strategies into this state space, represented as circles here, wherever they believe they would be helpful. Users then move through the space and provide relevance feedback, either enforcing the system and encouraging it to make more similar suggestions, or in different locations potentially also rejecting the guidance and teaching the system that this suggestion would have been better in a different context. In this way, users move through the analysis state space during their analysis and constantly teach the system what their preferences are and how they would like to be guided. Strategy-based guidance has this adaptation and this reaction to user feedback as one core principle. Let's look at the model in a bit more detail next. The analysis context vector, here in yellow, holds any information that might be relevant for guidance generation. This could be data or different models that are needed during the analysis. The guidance strategies themselves then become central system components. Each of those strategies is always given a context vector, a representation of the state space, essentially the position of the user in this rectangle that we saw before as the input, and has an associated guidance action that's actually responsible for generating the suggestion content. And we'll see in a second why this distinction is needed here. Of course, in an actual system, there are multiple guidance strategies. So we also foresee a component that orchestrates all of the strategies and resolves potential conflicts, for example, in timing, or if two competing strategies would undo each other's actions constantly. The produced suggestions are visualized in the VA workspace, and the user previews them with respect to their current analysis goal and provides relevance feedback depending on whether they like or dislike the suggestion. This relevance feedback loops back into the system through the guidance loop and influences the timing and content of the upcoming suggestions. At the same time, this relevance feedback also goes through the inference loop, which is used by the system to reevaluate which strategies are currently useful and activate or deactivate them to suit the user best. This guidance and inference loop both have a lot of theoretical background, so check out Ignacio's paper from Euroviz this year if you're interested. In the remainder of this talk, I'd like to focus on LOTSE, our implementation of the model in a framework that you could use in the next guidance system that you implement. We envision that you begin by designing guidance strategies as design documents that specify which guidance you would like to provide before specifying your strategies in YAML files. LOTSE then parses those YAML files and generates actual running extensible Python code that produces the suggestion, which you can integrate into your existing applications, both on the front end or back end side, whatever you prefer. As I said, strategies and actions in LOTSE can be specified as YAML files or could also be implemented directly as Python code. What they always have in common is that they define a lot of callbacks. For example, an applicability filter that LOTSE frequently checks to verify whether the user is at the correct position in the analysis state space for this strategy to produce new suggestions. Further, there are callbacks to generate the actual suggestion content, as well as further callbacks to handle acceptance or rejection of the suggestion, or previews and other things that users might do to suggestions. LOTSE then handles all of the typical guidance boilerplate code for you. It checks the contexts for strategies and actions that might be applicable. It processes relevance feedback that users provide. It makes and retracts suggestions, and so on. And to enable true mixed initiative guidance, it also features two timers, the guidance and the inference loop, that operate also when the user stops interacting with the system and use WebSockets to still push new suggestions to them if that's needed at the moment. In the paper, we also have a few usage scenarios that highlight how LOTSE can be used in different ways to implement adaptive guidance of different sorts, as well as two first use case studies with visual analytics designers that show that Lotse actually offers a lot of flexibility because it does not impose any restrictions on the types of strategies that you can implement while still being relatively easy to use. So, to summarize, I've briefly presented our implementation-centric model of guidance, as well as Lotse, our guidance library that allows the specification of guidance strategies as YAML files and then generates running guidance systems from them. We hope that Lotse can be an inspiration, maybe also a first step towards a grammar of guidance similar to Vega, which would further facilitate guidance implementation in the future, of course. The library is available online on GitHub and on PyPy with various examples and integrations into D3, into Vega, both with Angular and React. So please check it out, and thanks for your attention. Hi everybody, I'm Fabian and welcome to my talk on Lotse, a practical framework.
Thank you, Fabian. Very great work. I'm curious, though, if you can comment on, so this specific paper focuses on like interaction that you can observe from either mouse interactions or things like interactions with specific data sets. But I know like in recent years, especially I saw it on Euroviz, where there's been some work now looking at facial expressions and lots of different things in terms of learning about what someone might be doing. And I'm curious if you can comment on whether or not you can expand to include stuff like this, or do you believe that the interactions you can observe is just enough? Maybe that will be just noise?
I think that the interactions that you can observe are a good starting point because they already contain a lot of information that might be helpful and support you in generating guidance. But in principle, this analysis state vector that we maintain could also hold facial expressions or other things that you are able to collect. Ultimately, what Lotse generates is just a bit of Python code that runs, and you can specify REST callbacks. And if you have an existing backend that does facial recognition or emotion detection, frustration detection, and so on, then this could surely all be integrated here as well. But arguably, we've developed it with interaction patterns in mind.
Thanks. We have some questions on Slido. I'm going to ask one here. This is from Kaiju. Is strategy data or task specific? If so, does this mean that a new set of strategies need to be manually created for a different data set or task?
I would say that the strategies probably correspond to the different tasks, yes. And then in the talk earlier, we heard about burrito fronts and different solutions that are available. And I like to think about the strategies as leading to one of those points on the Pareto front, or maybe you need to combine different strategies to achieve a good result. So ideally, of course, it depends on the strategies that you really design. But I don't think that they should be task specific. But surely there will be different strategies that are needed and that make more sense for a given set of tasks than for a different set of tasks.
Thank you, Fabian. There are some more questions that we're going to post on Discord. So if you have time, it would be great if you can respond to them. Thank you again. Let's
Sure.
thank our speaker.
You.
Okay, so our next paper is an award-winning paper. And this is, I want to present the award for Best Paper Honorable Mention for Medley Intent-Based Recommendations to Support Dashboard Composition.
We actually have to do it all. Right. Good afternoon, everyone. First off, it's great to be back to doing this live in front of all of you here, as well as everyone watching remotely. The one downside, though, of doing a live talk after about 3 years, I feel as unsure about what I'm going to say next as all of you. So I think we're going to have to discover this together, but let's see how that goes. I'm Arjun Srinivasan. I'm a member of the research staff at Tableau. And today I'll be talking about joint work with Aditya Pandey and Vidya Setlur on using intent-based recommendations to support dashboard composition. Now, I think we can all agree that dashboards are one of the most commonly used interfaces to interact with data. But that said, dashboard authoring remains a fairly complex and underexplored topic, especially in visualization research. So to this end, we started this work by interviewing dashboard authors and identified two primary scenarios in which dashboards are created. The first and more popular one is a targeted scenario where end users or consumers of a dashboard provide a set of analytic goals or intents that they're interested in using a dashboard for. The second one is a more open-ended scenario where the authors of a dashboard work on their own to explore a new data set or a domain and specify what goals they are interested in the dashboard focusing on. Now, while it's not always as linear a process as the slides display, in the first targeted scenario, authors typically use the goals provided by the end users to select the set of views that are relevant to the dashboards and then compose them into a logical layout to create that dashboard. In the second open-ended scenario, authors typically explore the data to find a set of views that might be individually interesting, then sift through these individual views to find groups of views that kind of go into a logical analytic goal or intent, and then using those groups, create a coherent dashboard. Now, while these two are two different scenarios, one common theme between these is the notion of analytic goals or intents that the dashboard would ultimately be optimized for. So building upon this, the core idea for our work was then to explore how we can leverage this notion of analytic intents or the goals facilitated through a dashboard to assess dashboard composition. Now, before I jump into too many details, I'll first show a quick demo of our prototype system Medley that leverages the notion of intents to provide recommendations during dashboard composition. And for this demo, I'll be using a data set about sales for a fictional company with the goal of creating a dashboard that helps me get a gauge for the overall performance of the company. So as I start here on the left, you can see that the system allows me to specify attributes or intents that I'm interested in, or I can look at the default recommendations. Now at this point, I don't really have a sense for what exactly I'm trying to create the dashboard with, so I'll go ahead and look at the recommendations. As I do this, the system comes back to me with a starter set of collections, or what we refer to collections as views and widgets together, which summarize different types of intents that I might want to look at with my dashboard, like the distribution of values, giving an overview of particular attributes, so sales in the top right collection, highlighting change over time, and so on. Skimming through these recommendations, I think the collection on the top right that focuses on sales can help me give an overview of the company's performance. So I'll go ahead and add a couple of views from that collection to the canvas. Now, looking at the change analysis focused connection on the bottom right, I'm also curious about how the company has performed over time. So what I'll do is go ahead and select change analysis as an intent to see other similar collections. Now, looking at the new recommendations, I can see the first collection on the left, which helps me perform yearly comparison of sales values here, but now also a second collection that helps me see sales and profit together on the same dashboard over time. Now, while I like this idea from the second dashboard of using both sales and profit on my second collection of using sales and profit on my dashboard, what I really want to do is perform an yearly comparison with profit. So I'll select that as an attribute on the left panel and see what the recommendations look like. Now, with this updated set of recommendations, I can add 2 views to my canvas that focus on the profit attribute and change over time, but also a widget that allows me to now select which year I'm going to be looking at the changes for. At this point, I can go ahead and clear my intent selection of change analysis to see other perspectives that I might have already missed out on while I was focusing just on change. So Medley again comes back to me with a new set of collections, including one now on the bottom left that shows the top categories for the profit attribute across the different dimensions in the data set. Now, I like the idea of having the most profitable customers for each year on my dashboard, so I'll go ahead and add that one in too. Now, at this point, with 5 views and a year picker widget, I have the content for a dashboard that can help me get an overview of my data set, but also perform yearly comparisons. I can now go ahead, adjust the layout to make it more presentable to an audience, and also test interactions between views that were automatically configured by the system while I was adding them to the canvas. And I can also test if these interactions don't work out well for me. I can go ahead and edit them using a lightweight direct manipulation interface built into the tool. Now, hopefully that demo gives you a little feel for what Medley's interface looks like and the different types of recommendations that it supports. And all of these recommendations that you saw in the demo are based on a set of heuristics that we defined by collecting a survey of about 200 dashboards. You can find more details about the heuristics in the paper, but what I'll do for now is walk through one quick example using the change analysis intent to give you a sense for how these mappings go into the tool. So let's take this system state from the demo earlier, where I've selected the attribute profit and the intent change analysis on the left panel. I have 2 views added to the canvas on the right, and then I get the 2 recommendations in the middle. So to go from this input to the output you see in the middle, the system performs 3 steps. The first one is that it goes through a list of all possible collection specifications to see which ones are relevant to the current set of input provided to the tool. So for instance, in this particular case, since we have the change analysis intent selected, the 2 change analysis focus specifications are shortlisted. Next, the system then needs to parameterize these shortlisted specifications by selecting the attribute sets that it needs to display. So for this, the system leverages a combination of the user input, which in this case is the sales and profit attribute, but then also combines it with statistical metrics to pick attribute combinations that collectively lead to more interesting views in the dashboard. And once this set of attributes are picked, the system then populates those collections that we saw earlier. And as a third and final step, the system then takes those populated collections and then ranks them or ranks the views within them so that they are most relevant to the user's actions. So as a couple of examples here, in the first collection, you see the map moves up in the rank because there's already a map in the canvas. And in the second collection, the charts that have the sales attribute in them are bumped up in the rank because through the user's input and the views added to the canvas, we can implicitly detect that sales is an attribute the user is interested in. Now, once we had this recommendation logic and the system around it built out, we conducted a user study with 13 participants to validate the utility of the generated recommendations, as well as get some general feedback on the system usability. All sessions were conducted remotely, and after about a 1.5 minute long video introduction to the tool, participants were given 2 types of tasks, emulating the 2 scenarios of targeted authoring and open-ended authoring that we observed in our formative study. In total, participants created about 48 dashboards across the study sessions, and in terms of feedback, they indicated that recommendations were both useful and relevant, but also insisted that in some cases, they provided ideas for composing dashboards that they hadn't thought about before they started the study. That said, there were some concerns, particularly around sort of the initial learning curve on the concept of intents and just understanding the different types of intents and objectives that the system supported, suggesting that there's some room for improvement in making the intents and recommendations more interpretable going forward. Speaking of going forward, besides some of these short-term improvements, there are a couple of more high-level interesting research directions that we think this work opens up. The first one is that in this particular project, we mainly focus on intents and views that fit the mold for this more kind of conventional analytics style dashboard. But that said, recent work has shown that dashboards can span this variety of intents, purposes, and even designs that are more than just interfaces for analytics and monitoring. So to this end, looking at how we can take our notion of intents but then apply it to these other dashboards that are more, say, creative focused or storytelling focused is an interesting direction for future work. Also, during the study, multiple participants noted that iteratively selecting these attributes and intents was getting tedious and hinted at the potential use of natural language input. So a second direction that we think is really interesting here is to consider how we can take current natural language systems for visualization that typically have sort of this one utterance and one output and response to that utterance, and expand that to start thinking about how we can go from systems that can take one input utterance but then spit out a set of multiple views and or widgets that can help people create more complete dashboards. To summarize, though, in this work, we highlight that first, intents play an integral role in dashboard design. And second, we demonstrate how leveraging these intent-based recommendations can aid dashboard composition. And with that being said, I'd be happy to take any questions. Thank you.
All right, thank you, Arjun, for a great talk. We have time for one question, and this one is by Marty Hurst. The question is, this is a cool solution for dashboard recommendation and construction. How do you know if the dashboard that is put together will be usable? Do the recommendations have any usability information associated with them?
So the way we derived the recommendations were through our survey. So we looked at dashboards that were already on Tableau and Power BI and were a shortlisted set. So we looked at ones that were specifically curated as the best of these tools by the companies themselves in typical cases. So these were, in some sense, the recommendations built into the tool already have good design built into them in the sense of the charts that they have and so on. But we don't have usability of the dashboard as a metric that we added into kind of evaluating the recommendations on the fly. But I think if we can collect a good enough data set that we can derive that metric for and feed that back in, that would be really interesting to consider going forward.
Awesome, thank you. So you will have some other questions on Discord.
Okay.
And yeah, thank you again.
And congratulations.
Thank you.
Okay, our final paper for the session is called Jevitrek, Data Reconnaissance Through Recommendation Using a Domain-Specific Visualization Prevalence Design Space. And this will be presented by Anna.
Then Jevitrek, an approach for data reconnaissance through visual recommendation using a domain-specific visualization prevalence design space. The process of gathering the right data set for analysis is often fairly complex. One source of complexity is that the analyst's understanding of the data set evolves over time. Here, a data set is represented by a little square, and the shading of the square represents the familiarity, which changes as the analyst progresses in their analysis. As the familiarity with a singular data set grows, an analyst might recruit additional data that they think is interesting or could augment their analysis. Over time, an analyst might see a reason to consolidate these different data sets, combining them at different points, trying out different combinations and rejecting them until once again they achieve a final data set that they might actually use for analysis. As this process evolves over time, analysts are constantly assessing what they've done, viewing the data, visualizing it, talking amongst themselves, until they finally arrive at an insight that they might actually act on. In a prior paper, we discussed this as a process of data reconnaissance, which is exploring an unfamiliar data landscape, one that is actually quite large and contains a lot of heterogeneous and multidimensional data sets that are not yet understood by any one specific person. We identified 4 steps: acquiring data, viewing it, assessing it, and pursuing new data over time. As we applied this conceptual framework of data reconnaissance to discussions that we were having with some of our stakeholders, we found that the step that was the biggest barrier was actually viewing the data by creating data visualizations. One reason why it's hard to do so is that these different data sets are actually able to be integrated by sharing common fields, but they're often separate, and so it's challenging to bring them together. For the rest of this talk, we're going to focus on the domain context of genomic epidemiology. Genomic epidemiology has a lot of very varied data sets that are often integrated together. Here's an example from the NextStrain tool, which is created by experts in both virology as well as very competent programmers. What you see in this visualization and what is achieved through a labor-intensive manual process is that These 3 individual data visualizations integrate information from across these different data sets and visualize them together. We took inspiration from these manual and intensive efforts and decided to explore an approach for recommending visually coherent chart combinations. These are recommendations that prioritize visual coordination of shared information between charts with respect to the layout and consistencies among visual channels. Okay, so why does this approach matter? Let's imagine you've got 3 data sets, a genomic, a spatial, and a tabular data set. You might begin by creating individual data visualizations from each of the data sets. Now, producing one chart at a time might seem easy, but then a person actually has to take all of these together and integrate shared information across them if they want to achieve this kind of visual coherence. We introduced a method called GevitRack that automatically constructs visually coherent chart combinations. It does not require the person in the middle. Now you might be wondering to yourself, hold on, why not just solve this with interaction? We have a lot of great techniques and approaches. We get into this a little bit more in the paper, but the short version of it for this talk is that it's still really useful to have visual coordination between channels and not necessarily just rely on somebody wanting to interact with the data. In fact, this kind of visually coherent chart combinations can augment and better support interactions as well. All right, let's get into the nitty-gritty. What is GevitRack? It's actually a multi-stage approach that takes in some kind of input data and automatically produces visually coherent chart combinations. The first step is to explode the fields of the input data sets. Here we have examples from phylogenetic, table, and spatial data. In exploding the fields, we extract individual data fields or attributes, and we analyze the nominal attributes to try to find some sort of overlap between the different data sets. We next use the analysis of the fields to derive a data source graph. This data source graph identifies commonalities between data source attributes, creates linkages between them if any, and classifies the type of linkage as exact, which is a perfect overlap between fields of multiple data sets, and inexact. Next, we analyze the paths of the data source graph. We do so by identifying all possible paths between pairwise combinations of data set, and we rank these paths by 3 criteria: the strength of their connections, the diversity of the data types, and the relevance of this data to the stakeholders. A key component of the ranking algorithm is a domain prevalence design space. This is something that describes common patterns, the way that people create visualizations out in the wild. For GevitRack, we've actually used a domain prevalence design space that we describe in a prior paper called Gevit. This allows us to understand not only the diversity of chart types and data that our experts use, but how they combine them and how they augment them as well. We next create visualization specifications by leveraging existing chart templates. We derive specifications for each path in the graph in rank order, and we do so by first creating individual chart specifications for the different dataset types, and then we automatically combine and align them using multi-chart specifications that is eventually displayed. We implement GevitRack as a proof of concept using the R programming language, which is a common analysis language that our domain experts used. In panel A, you can see the 3 GevitRack commands that it takes to actually produce a recommendation. In panel B, we show a visualization of the data source graph that is automatically computed by GevitRack. And in panel C, we show its top-ranked recommended view. The top row of the top-ranked view shows positionally aligned chart combinations. If you read horizontally across from the leaf nodes of the phylogenetic tree, you can see additional information in the scatter chart as well as the little heat map. GevitRack can also recommend color alignments between charts. Here we see the colors between the phylogenetic tree as well as the case counts in these different nations are coordinated. Finally, we can also see coordination between the different fields that are used in the visualization, either as axes or to color or things that appear in the legends. You can see more examples and more data sets in our supplemental materials. Even MT cars, our favorite reference data set, makes an appearance. We compared GevitRack to existing systems for both automatic visualization recommendation and manual curation. If we take a look at our tools for automatically recommending chart combinations, they are relatively easy to use, but they only suggest one chart at a time. There's still manual curation that's required to achieve any kind of alignment, and there's limited support for variable data types. Really only tabular data and in some instances spatial data is supported. If we compare GeovetRack to those manually created by experts, we see that the expert tools really do have better alignment between chart types. Like GeovetRack, they also support multiple types of data. However, these manually created visualizations require much more extensive labor. They can also be less adaptive to underlying changes in the data. Lastly, we evaluated GeovetRack through semi-structured interviews with 10 experts in genomic epidemiology. We conducted chauffeur demonstrations of the GeovetRack tool using both a synthetic and a real data set. Participants said it was valuable to see the data source graph so that connections between data sets can be seen together. They also found it was relatively easy to interpret visualization recommendations, that it was useful to have a menu to choose from, and that some of the redundant encodings helped them tease out different aspects of the data set. They also felt that the tool provided really useful visualizations, especially for data exploration when data are incomplete and highly variable. Finally, some participants wanted to see further customizations, specifically tailoring top-ranked views to particular research questions and allowing the lower-ranked views to be more flexible. All right, let's wrap up by going back to where we started. The fact that gathering the right data set for analysis is a complex task. GeovetRack addresses some of these challenges by lowering burdens to quickly visualize data. It does so by automatically identifying connections between datasets and using these connections to recommend visually coherent chart combinations. This reduces the need for extensive manual curation and fundamentally speeds up the process of data reconnaissance. There's a lot more to GeovetRack that we did not cover here. We recommend taking a look at our paper for additional details. Thanks. We present GeovetRack.
Hi, Anna. Thank you so much. This is such an impressive project. I'm curious, though, if you can talk a little bit about how you might think about customization. So I ask this because of two things. One, like your participants mentioned customization, but then you also showed the expert created dashboards and said that the layout was a little bit more intuitive and better. And I'm curious about like how you might think about the next generation of this tool for further customization or adaptation.
Yeah, I think that we can think about customization in two ways. So one is that GeovetRack would provide a base of like visualizations and could expose those specifications to an end user that wants to tweak them a little bit more. And so in this way, kind of overcoming a cold start problem that might exist when you're looking at a bunch of data sets. And this could also allow for the customization that comes from the extra level of curation that sometimes human input adds. So GeovetRack provides base to get you there faster, and then maybe get to 80% of the effort, and then the other 20%, we can decide what we expose to the end user. The other kind of customization that you brought up and that the people wanted as well was further, I'd say, more personalization based upon the particular data question that they had. I mean, I was at the VDS keynote where Remco talked about exploring the hypothesis space of a data set as well. And so one of the things we're doing here in this work is we're actually traversing and exposing potential visualizations in the data space, but there might be really fun and interesting opportunities to then combine that with a potential hypothesis space that allows that level of personalization as well. So to sum up, two possibilities: customization, GeovetRack gets you 80% of the way. You figure out what you expose to get that other 20% of reducing the manual load, and then personalization by exploring both the data and hypothesis space together.
Got it. So I didn't realize that you saw Remco's talk, because that's the question I really wanted to ask.
I did. Of course I saw his talk.
But okay, so we're out of time, but there are two more questions. The student volunteer will post it on Discord. If you have the time, please take a time. Please go and look at it. And I guess Tamara is also here. So if anyone has questions, hopefully she'll be willing to answer them. All right. Thank you so much again, Anna. And thank you guys for spending the session with us. I hope you enjoy the rest of your week.